In this lesson, we're going to be talking about the factors that affect climate. You should have printed out this handout. So this is where you're going to be taking your notes. This will be your study guide for the test. So you'll want to make sure that you have this. So we are going to be talking about climate. To start off with, though, we're going to talk a little bit about the difference between weather and climate. When we talk about weather, we're looking at something that is passing. We're looking at what is it like out today? Is it sunny? Is it raining? Is it cold? Is it warm? What is the weatherman telling me that it's like? We're looking at just in my area. So we're saying, I want to know what the weather is in Phoenix. I don't want to know what the weather is in all of Arizona today because I can't say, they can't just say what the weather is for all of Arizona, right? They can talk about the different areas of Arizona because being in Flagstaff is going to be very different than being in Phoenix. Weather conditions change pretty rapidly, whereas climate is a very slow change. Because climate, we're talking about long-term averages. We're talking about data that's been collected over many, many years. And it's something that doesn't change very quickly because once you have 100 years of data, it takes a lot in order for that to change, to say that our overall trend of what things are going to be like will change. And in this one, though, we can talk about bigger areas. So we can get climate data for Phoenix, but most often we talked about, like, what's the climate like in the Sonoran Desert? What's the climate like in the Mojave Desert? What's it like in the Cascades? We look at bigger regions usually when we talk about climate. So we're going to look at different factors that affect climate. We're going to talk about what each of these are and how they affect climate, and some examples of each of them. So while it's important to know what the factor is, the main thing that I want you to be writing down on your paper, if you don't know what it is, obviously write down what it is, but what you really want to capture on your notes is how does that factor affect climate. So latitude, for example, is that distance north or south of the equator. So we're looking at these lines here on the globe. Okay, our distance north and south of the equator. But because of the way our planet goes around the sun, the equator gets the most direct solar radiation. So it's kind of like sitting at a campfire and putting your hands directly over the top of the flames. When your hands are up there, the heat is coming directly at your hands. That's the most direct spot where you're going to get the most heat. And it's really hot there. Being up here in the northern latitudes or down here in the southern latitudes, it's more like having your hands on the side of the fire. You're still going to get warming, but you're not going to get as much as you have over the top of it because you're getting a more diffused heat from the side. And that's the same thing that happens with the sun. Because it's not pointed directly at our polar regions, they don't get as much of that heat. It's kind of like having your hands to the side of the fire, and so those areas tend to be colder. So for example, we're going to look at Canada and Brazil. So Canada is up around, we're looking at around 75 or 80 degrees north latitude. 90 degrees is up at the pole. And then Brazil, which depending on where you're at, could be anywhere from at the equator to just above, or it can go, actually Brazil goes quite far down below, but we're going to look pretty close to the equator in this example. So in the wintertime in Canada, we get the pretty mountain scene. It's very cold. Um, the temperature drops well below zero in those areas. But when we look at Brazil in the wintertime, now if you look at these numbers and you say, oh, but look, it says 37 degrees. Well, but that's not in Fahrenheit. That's in Celsius. And 37 degrees Celsius is about 98.6 degrees Fahrenheit. So in the wintertime, we're still looking at really warm temperatures. You'll notice that there is a difference over here on the coast, and we'll talk about why that is in a few minutes. Please understand that while we're going to talk about these factors separately, all of these factors combine to create the climate of certain regions. None of these factors are acting in isolation because Earth is a system, so all these things happen together and in concert with one another. This map is a thermal reading. It's a colorized image showing our warmest areas on the planet closest to the equator. The equator runs right through here. So showing our warmest regions in red, our coldest regions in black. The next factor that we're going to look at are global winds. We talked about these before. These are our big wind belts that go around the planet. Remember that the wind belts happen because of the Coriolis effect and because of the unequal heating of our planet. Um, But when we talk about how does that affect climate, the global winds are they're like the vehicle for weather to move around. So they're going to move storms around, which causes rainfall. Okay, so without our global winds, we wouldn't have these patterns of movement of moisture around the planet. So they're really important because of that, because it's that distribution system. Looking at our different winds again. We talked about topography when we talked about the rain shadow effect with weather. We said that how does topography influence our weather? It's the same way it influences our climate. So we talked about that if the ocean is on this side of the mountain, that the air is nice and warm and moist, and as it gets pushed up, it cools off. It can't hold as much moisture anymore, so it condenses when it reaches its dew point. Rain starts to fall, and the rain will fall mostly on the side of the mountain where the ocean is, or the windward side. And then as the air moves down the leeward side, or the non-ocean side of the mountain, it can start to expand as it goes down. It gets closer to the surface. Um, excuse me, it doesn't expand, it compresses together. The particles get pushed closer together. The temperature goes up, which means that it can hold more moisture, which means it's drier down on the side, and so we don't get as much rain. And so we have a wet side and a dry side of the mountain. And this influences our climate pretty dramatically. So this is the Cascade Mountain range. So this is the high area here. This is the ridge line. Then you go across the top here, and all that green is all of our vegetation. And the ocean is over on this side, over here. So the clouds got pushed up, the rain dropped, created all this great vegetation, and then as you move down onto the leeward side, there wasn't as much moisture available. Now, this isn't desert on this side of the Cascades. If you notice all these little squares in here, those are all fields. What it is prairies, and it's actually an area where there's a lot of farming that happens in the eastern part of Washington and Oregon. This example here is the Big Island of Hawaii. So this is the windward side over here. So the clouds get pushed up. That's what this is right here. These are clouds. They get pushed up. Precipitation happens. It's dry as it goes down this side. And this one is so dramatic because the rain, not only does it help vegetation grow, but it also breaks down the rocks, which made soil, because you have to remember this is volcanic. So it actually had to turn the rocks into dirt in order for stuff to grow. And so it sped up the breaking down of the rocks and soil formation as well, which is another reason why this one's so very dramatic. So elevation will help determine temperature also. Remember, elevation is the height above sea level. So the higher you go, the more your air is expanded because there's not as much gravity holding it together. And so the air pressure is less. And when the air pressure is less, remember we talked about high air pressure, meaning that the particles were close together, and it was like rubbing your hands together, right? And that friction caused heat. And as we go further away from the surface of the planet, we get less air pressure. So it's like your hands are getting further apart. There's less friction, which means there's less heat. So this first example is Denver, Colorado. And in Denver, it's at 5,200 feet above sea level, so it's a mile high. That's why they call it the Mile High City. So it's pretty far up there. You'll see that while the temperatures get up to about in the high 70s in the summertime, it gets kind of cold in the wintertime in here. And if we look at and we compare that to Death Valley, depending on where you're at in there, some areas, depends on if you're in some areas of Death Valley, you can be actually 86 feet below sea level. These data readings are coming from an area that's 167 feet above sea level, but still we're looking at 5,000 feet below Denver, Colorado. And this graph is just a little bit different, but I want you to look at this red line here. That's our maximum high temperatures, which is what this red line here shows also, is maximum high temperatures. And so you'll see that in July, in Death Valley, our maximum high temperature, the average, is 114.8, so almost 115 degrees. And in here in July, it was like 78. So that elevation factor makes a big difference in those average high temperatures. Our next factor we're going to look at is the proximity to a large body of water. What this just means is how close you are to a large body of water. And we're talking about like an ocean or the Great Lakes. We're not talking about like Lake Pleasant. That's not a big enough body of water to make this difference. So in order to understand why this is, we have to look a little bit at the properties of land and water. The ability for a substance to hold on to heat is called specific heat. And land does not have a very high specific heat. It heats up and cools down really quickly. So that makes it so that the temperatures in a region will vary greatly from summer to winter and even from day to night, because the heat just doesn't get retained in the area. And so we can have areas that are really, really hot in the summertime. They could be over 100 degrees in the summertime, and they could be below freezing in the wintertime. Whereas if you're next to that body of water that holds on to the heat longer, it makes it stable. So it's not necessarily that the coastal areas are going to be warmer or cooler, it's that they're going to be more stable. So if they're in an area that's predominantly cold, like the northern regions near the Arctic Circle, it's going to stay cold and it's going to stay consistently cold all the time. If you're in a warmer region where you're near the equator and you're near a warm ocean current, then it's going to stay hot all the time. It's just going to keep it much more consistent. So we're going to look at San Diego and El Paso. San Diego is at 30 degrees north latitude. El Paso is at about 31.7 degrees north latitude. I know they don't look the same if you're trying to draw this line straight across, but when you're looking at a map with latitude and longitude, you have to remember that we're trying to put something that's from a globe or a circle onto a flat surface. So you have to follow the curve or the arc of the line. Okay, you can't just go straight across. So they really are at just about the same latitude. And when you compare them, this first data chart is El Paso, and you can see that there's a temperature swing, okay, because it's in the center of the continent. El Paso, if we go back to here, El Paso is pretty far away from any body of water, and so it's not going to moderate the temperatures for El Paso. San Diego, on the other hand, is extremely consistent. You're going to go from the high 50s to the low 70s pretty much all the time. You see very little change in the temperature because that big body of water is keeping it consistent. So our next one we're going to look at is ocean currents. We talked about this a little bit already, but ocean currents, if it's a warm ocean current, then it's going to warm up the air above it through conduction, because that air is going to be touching the warm water, and it's going to transfer the heat into the air, and so the air is going to blow onto the land, and you're going to have a warmer climate. If it's a cold current that's going past the land, then when the air touches the water, it's going to be cold, and that's going to blow onto the land, that's going to make it cold. So it's whatever the current is going to transfer that temperature pretty much to the land. So when we look at our ocean currents, we have some currents that are warm, some currents that are cold. And I want you to look at the United States here. We look at our west coast. If you've ever been to the ocean on both the west and the east coast, you'll know that the west coast, the ocean water, I mean, the ocean water is cold anyhow, but it's just the degrees of cold. But we have this cold current that's going down the coast of California that really does cool it off. We see great things because of that cold current coming down. That's why we get to see the ocean migration of whales and things like that, which is really cool. We also don't have as big of a continental shelf, and that also keeps the current cold in that area. As we look at coming up the east coast, we have the Gulf Stream that comes up here, and that's the reason why we have such moderate temperatures on our east coast. You can see that where the Gulf Stream starts to take this curve out into the Atlantic Ocean, this is why the southern part of the east coast is so much warmer than the northern part. And even where you get to where the latitude's not all that different, as soon as this right around Washington D.C. is where it happens, you get a little bit above Washington D.C. and you're not that far away in latitude, but you no longer have that warming ocean water. Now I also want you to see how it goes across, and this is the United Kingdom right here, because we're going to look at this in just a second again. Here's our Gulf Stream. So here's Washington, D.C., and you can see where the Gulf Stream starts to take this curve out. And that's why we get such colder temperatures up here. So we're a little bit further north in latitude, but we also don't have this nice warm water going past there. So I said I wanted you to pay attention, right, to that current going past the UK up here. So this warm, nice current comes over here, this way. And we look at these two cities, and they're at the same latitude, pretty close to the same latitude. There's ice over here. Look at this, ice all the time off of Newfoundland. But over here, it's really nice. So when we look back at our currents again, we see the Gulf Stream comes all the way across to the UK and keeps it nice and warm. And that's the only reason that they can have agriculture there. Look at how far north they are. We came across in here into Siberia. This is Siberia, right? It's in Russia. It's cold. It gets really cold, and it takes a long time for it to warm up. But the UK has a lot more agriculture because they have this nice warm current over here. Over here in Newfoundland, the Labrador current, which is kind of underneath my arrow a little bit here. A little bit underneath my arrow, there's this blue Labrador current that comes down here that's really cold, and it's coming right down from the Arctic, which is why they have ice there all the time.